All right, good evening, everyone. Welcome to this problem-solving workshop on array-based questions. The goal was for this to kickstart the SDE Skills San Francisco group. I know we've been struggling to meet in person. My whole goal is to actually do more of in-person meetups and get people to get started. But then, given that we've been struggling with this, we'll be working through these questions online for now, and then we'll find a way to make this happen. And folks, if you are if you're not speaking, please go on mute. I've just muted one of the participants. If you're noisy, I'll just mute you. It's just hard that way. I can unmute, but then the challenge with that is that I don't think you can. If I mute you, you can't unmute. So Sandeep, I've just unmuted you. Please go back on mute. Yeah, fantastic. And if I have muted you and you want to unmute, then please just ping me on the Slack or ping me on the meetup. I'll unmute you as well. All right, so let's get going. There are a bunch of folks who are just joining at this point of time, and some of you may not know that you need to join the audio bridge as well because this tool is new. Please join audio bridge. I'm hoping that people see that. Okay. All right. So first question. Let's get started. So this is a classic n-sum question. The most common format for this is the Twosome problem, which is given an unordered array of integers. So we talk about integers, and it is unordered in the sense that they are not in any specific format. It's not sorted. Your goal is to actually find two numbers in the array that add up to a target number. So for example, if you're given an array of something like 1, 5, 7, 3, 2, 9, and if I wanted you to find something that adds up to 11, what would that be? It would be essentially 9 and 2. That's the Twosome answer, right? If I ask you to find out that adds up to 8, what do you think is the answer? Anyone?
7 and 1.
It could be 7 and 1.
Or 5, 3.
Or 5, 3. Anything else? I think that's about it, right?
Yeah.
In this combination. So the challenge in this particular scenario, the expectation would be for you to return any combination that is possible. Not all, but any solution is okay. And the type of the solution that you choose will actually vary subtly based on that. So if you are in an interview situation, do ask a question in terms of clarify with examples, clarify with what happens if I ask you how to make 50. Clearly you can't make 50, so you return like null or empty or like exception or something like that. That will be the expectation. Okay. So any thoughts on how you want to solve it? So let's actually walk through some solution approaches, and then we can talk through trying to code them. Any thoughts?
The basic order of n square operation,
Okay, you can do an n square operation. How? Walk me through the n square solution, please.
N square solution will be like there will be like two arrays, one outer array and inner array. The outer array will start from 0 and go to less than length of array length minus 1, and then the inner array will be the I plus 1, and then the j less than array dot length, and then you can check if a of I plus a of j equals to sum. If you can, you return it. If not, at the very end of the loop, you can return null.
Yeah. Okay, makes sense. So that makes sense. So that's an n square operation. What is the space complexity of this thing, the solution?
There is no additional space here, right? But the thing is just the number of operations are high because of because you're not like storing anything. And as soon as we hit the you're just like doing the calculation. As soon as you hit it, then we're just going to return that.
Correct. So what is the space complexity of this?
1? I don't know.
It is O of 1.
Yeah,
Correct.
1. Yeah.
I mean, the whole, I'm just like walking through this so that we are kind of clear, right? So the way this works is that you are actually not using extra space. How this is working is that you are actually using just constant space, just a few variables and nothing more than that. Just 1 second. Yeah, folks, I am actually indiscriminately muting you if I'm getting feedback from you. Let me know if you need back, get back on this. Just let me know. I can unmute you as necessary. Okay. All right. So that's n square operation. How can we do better than that? Can we do better in terms of space? Let's assume that you have infinite amount of space available. You can do whatever you want with space. Can you actually still manage? Can you do it faster? Anyway.
N solution is possible if you have space.
Can you say that again?
N solution may be possible if we have enough space.
So let's assume that you have enough space. Go ahead. Tell me how you do that.
Say we iterate through the array once.
Oh, you have a lot of background noise. Sorry. I'm able to barely hear you, unfortunately.
I'm at home. I can't help it.
Sorry about that. Yeah. Maybe somebody else can actually take a lead at this, and then we'll circle back with you, Datta.
I was thinking if there
Can I attempt?
Yeah, go ahead.
Yeah. So the first solution that was given was basically O of n square. So in which we were doing so we were iterating in the first loop, and then again we were iterating again. So basically we were doing the same work twice. We were seeing each element twice, right?
Correct.
So what we come up is we first write the brute force, and then we see how we can optimize that. So in the second loop, what we can do is we can create a hash set in which we store all the elements which we have seen before, and then in the second loop we can check if the element is already present or not. We've seen it, so we check if there's an element of target minus num already present in the hash. If it is there,
sure. So that will work. It's a good strategy, and we can walk through that. What's the time complexity of this operation?
It's O of n.
Okay. And
I have
space?
a question here.
This is O of n as well.
What was the question?
So if we do a hash set, it is, suppose if we have same number twice, like if you have 6.
We'll come to that. We'll come to that in 1 second. We'll get together. I'm just getting the high level ideas, and then we'll walk through each of the solutions to some extent and talk about the nuances in each of them. I think the hash set does suffer from one limitation which you can solve in a few different ways. So we'll come to that. Okay. And good catch on the duplicate element duplicate element piece. The third part of it is what if I were to tell you that you don't have extra space, but you are permitted to rearrange the elements in your own way?
I think in that case we can sort the array, and the total time complexity for sorting would be n log n. And then we can start to check for the elements from, we can have 2 pointers, one on the lowest element and one on the highest element. And then we can start adding them to see, if they are equal to the target sum. If that's lesser than the target sum, the lower pointer can be moved 1 pointer ahead. If the total sum is lesser than the target, then the right pointer can be moved. And this can be done until the left pointer is lesser than the right pointer. The index of left pointer is less than the index of right pointer. So I think the total complexity of this would be n log n, but it might not need any extra space.
Is it n log n? Is there, do you want to be a little tighter with that? Is it just n log n plus something? And then, of course, you can ignore that, or is it n log n directly?
Oh, yeah. So that way it would be n log n for rearranging the array, sorting the array, and then O of n for traversing the array. But then since O of n is lesser than n log n, we can
just ignore the n and just say it's n log n. Correct. Fantastic. So there are like 3 different techniques of doing it, and I generally put it in the order of time complexity. So the simplest option is essentially to do n square, where you really don't rely upon anything else, no extra space required. You can just go through the whole array, loop it, and then you get it. So that's like the simplest answer, and sometimes that is the only answer. Like as an interviewer, I've seen this question being beaten to death by, sometimes they start with like, hey, tell me how you'll do it, and I've seen people come up with like the O of n solution with O of n space, and then they come back and say, what if you don't have extra space? Then you say, can I rearrange the array because I can sort it? I've seen people come back with saying, no, you cannot even rearrange. Then what do? You don't have a choice but to essentially go through the n square operation where you are just going through it over and over again, and that's pretty much how it works. So that's the path. So let's go through the most optimal O of n solution first, and I think Ankur was talking about one sidebar that Anita was pushing back on was saying that what happens if you have duplicate elements, because essentially if you have like say 1, 2, 5 and say 8, right, or 1, 2, 5 and 6, and you wanted to find if 10 is there. So there are two ways of actually solving this. One is essentially you take a O of n pass first to load the entire array into the hash map first, and then you go as a second pass, and then you just go and check if the complement of what you're looking for is available in the hash set. So that's kind of what you look for, and that technique suffers from the issue that in this case, do you see 2 5s available? No, but then the question is like, do you have you want 10, and you're checking if 5 is in the hash map, you will probably find it. So the complement, it becomes an issue. So the technique that Ankur was talking about was essentially what you do is that you're actually going to say for the element in the array, first you check for its complement, right? If you say so if the hash map of get target E, if it's there, then essentially you have found it, right? And if it's not there, found it, and you can just exit, right? If it's not there, then what you do is then you add it to the hash map. Hash set, not map. Why would you use a hash set versus a hash map?
So basically, whenever you have key values to be stored, you would go ahead and use a map, and whenever you have just set of elements to be stored, you'll go ahead and use a hash set.
Fair enough, and please be careful when you're using that, because it's very common and logical for us to kind of use hash map everywhere because that's what we kind of do. But in this case, if you use a hash map, that will not be good, because there is no reason for you to add have that, right? That's all. So Anita, this is how we would do this, where you would go through every element. If the hash set contains the target minus E, then you have found the answer, and if you don't find the answer, then you just add it. So what happens in this case is that it will fail. This will not find the answer for 1, 2, 5, 6. However, if you had 2 5s, the first 5 will fail, right? Because you don't have 5 in the hash set yet. But then you will add the 5 to the hash set, and the second 5 will succeed, because you would have added the complement at that particular point of time. So it's a kind of interesting way of doing it lazy, like loading the hash set after you check for the complement, and that way it actually works very well. Any concerns? Any questions, Anita or others?
No, I was thinking about asking about like, can we use the same element twice?
You can't use the same element twice. Good point, SB. So the element has to be there twice for you to be able to use it. And the only way that works is if you, for hash map, there are two ways you can do it. One is essentially use a hash map and keep a count of the numbers and then try to do something with it. Or you could do this scenario where you're actually just simply looking at loading the hash map or hash set only after you check if the target is there or not. So that actually works very well.
And this won't work if for a 3 sum or an sum, right? I mean, like,
that is correct. So we will extend it as we go, and we'll figure out how that works, right? So this is Twosome. Very simple, very straightforward. The sorting technique is something that I think people have also understood. It's essentially you just sort it, and what you're saying is that you keep one pointer here and one pointer here, and what you see is that what's the total of 6 and 1? It's 7, which is less than 10. So you move the lower pointer to this, and that essentially makes it 8. So that's still more. They're still less than 10. So move it here. This is 11. Since 11 is actually greater than 10, you move the right pointer inwards. So essentially what you're trying to do is, since it's sorted, you're starting from both extremes, and now what you're saying is, if the answer I'm trying to find is exactly the sum of the first and the last element, you found an answer. But if it is not, one way to find a larger number than what you have right now is to move the left pointer inwards, and one way to find a smaller number is to move the right pointer inwards. And so that's kind of how you would figure out which pointer to move depending on whether it is smaller or greater, and that should get you an answer. And that solution, the answer is not found when both the pointers actually kind of collapse. Right? They both join the same. Both the pointers are in the middle. So assume that this was another 6, right? Then what will happen is it's still like 11. So then both pointers will be overlapping at this point, and you know that you don't have an answer anymore. Okay, so that's the twosome technique. So let's take a few minutes to kind of go over how would you extend this for threesome. So let's assume that now I'm saying we don't want to do twosome. I want you to find 3 numbers that add up to, say, 13. Okay. What are the answers here, please?
5, 6, 2.
5, 6, and 2, and there's also one more answer, right? Which is 1,
8, 5. Oh no, 3 numbers,
1,
right?
6, 6.
Okay, yeah.
166 is also an answer.
Okay.
So in this particular data set, I have 2 answers, that is for threesome, right? So how would you figure it out? What would be the algorithm that you would use to get to this? Let's start with the brute force. What's the worst way? What's the O of 1 space way of doing it?
Sort the array first.
O of 1 space. So sorting is out of the question.
O of 1 space. Okay.
So it will be order of n cube, right?
Correct. Very similar to how you did the n square technique. Yeah. This will be n cube time. And why is it n cube time? You run 3 loops, nested 3 loops for I equals 1 to n minus 2, n minus 3. For j is I plus 1 to n minus 2, and then for k is j plus 1 to that. Yep. Anyway, go ahead. So go ahead. What do you think?
So is the array sorted, or is it like unsorted?
No, it's not sorted.
Yeah, cool.
So n cube, right? So let's assume you can sort the array. How do you, let's assume you can sort the array. Let's start with that. So if you sort the array, that's n log n, right? How will you figure it out? Now let's assume you can sort it. Now what's the solution?
So basically, like, you take one element, and you find the 2 elements based upon the twosome problem with 2 pointers. Right.
So you have your array of x number of elements. So what you do is you run a for loop, which essentially starts from the first location, then starts from the second location, starts from the third location, starts from the fourth location, and so on. While you're doing that, you're actually, so this is your first element A. You're trying to find B and C, so you just solve the twosome problem
for B and C.
For B and C on the right half of the array, right? So what is the time complexity of this operation?
N square.
It's one loop for A, which is n, times, we know that the sorted twosome problem is O of n, right? Once it's already sorted.
Yes.
So it's n square. And what about the sorting?
N log m. So we sorted at the first, so n log n plus n square.
Yeah, and which one will stay?
N square.
N square is actually worse. So essentially it's just n square, right?
Yes. Yes.
So for 2-sum problem, extended to 3-sum problem, you're just doing this. Now how do you extend this to a 4-sum, 5-sum, and so on? Just using the same sorting technique. You just sort it, then essentially you find A, and then you solve 3-sum to find B, C, and D on the right half of the array, and that's it. Or you solve.
As when you increase more n's, the complexity increases by n.
Correct. So essentially, it's n power k minus 1, right?
The k is the n-sum problem.
Where k is essentially it's a k-sum problem, unfortunately.
Yeah.
Right. So if you're trying to solve the k-sum problem, it's essentially n power 1 if it is k is 2. So 2-sum is n. But the problem is that this is essentially n log n plus this. So if k is 1, then this n log n is meaningful. If k is more than 1, if k is 2 or higher, 3 or higher, then this n log n is just goes away, and it's just n square. The sorting is not that expensive anymore, right? Yeah. So that's one way of looking at it, and that's one way of solving it. Now let's actually try the other technique, which is like the Hashmap technique, right? So let's do the Hashmap technique, and let's actually do 4-sum, right? So the fun thing you can do here is what if you, instead of actually putting in the hash set, instead of loading all the elements in the hash set, what if you actually loaded all the pairs of numbers? Like do a double loop I comma j, and then you load all combinations of a of I plus a of j into the hash set, into the hash map. Call it hash set for now, but you could potentially load it into a hash map, and as a value you can actually just keep the I and j values stored.
And then you load up to k and the other two values.
Yeah, L and M is what you need, right? So this gives you got 2 of these, then you need the other 2. So you can actually now look up this one as a 2-sum problem.
Yes.
But 2-sum problem of what order? The number of elements here are n square, right?
So do we need like 2 hash sets in this place, or
just one?
Just use
one. It's the same hash set, right? There's only one hash set, and in that hash set you put all the combinations of a of I plus a of j values, and there will be n square elements in that. Correct?
Right.
N times n minus 1 variables in that, but yeah.
Yes, exactly.
And those values are all, that's n square, and now you're trying to solve 2-sum problem in that set. Correct? There is only one issue with that, which is
the duplicates.
Not duplicates, but what if your solution needs those duplicates? For example, if I have like 1, 2, 3, 4, and 5, if this is what I have, and your solution actually requires essentially say 3 plus 4 plus 5 plus 5, for example, right? So this is what? 17. If I wanted you to find 4-sum of 17 in this data set, there's no answer because you don't have 2 5s to deal with. Right? That's not possible.
Okay.
However, in your squared hash set, you would have actually stored 1 plus 2, you would have stored 1 plus 3, and so on. You would have stored 3 plus 5, and you would have also stored 4 plus 5. And then you would have picked this up as 8, and you would pick this up as 9, and then you would essentially say that these two add up to 17, and you're good. You're golden.
Oh, I see.
Right?
So it's basically like you go through the values of the hash set and you find the corresponding 2 values that add up to 17, and you see their respective keys, and you pick up the I and J and LMN values.
Just to make sure, look at all the keys to make sure that you have unique keys. Otherwise, if there are duplicate keys, then you ignore that combination.
Right.
That would be the way to solve this. So what is the time complexity of, so 4-sum using the sorting technique that we did earlier essentially is a n-cube solution, right?
Right.
4-sum using this sort of the hash map technique is what?
So to load up every single element into the hash map, you're like n into n minus 1 times.
So n square.
Right. And then the space complexity. Now you're going again with the values of it, which is like order of n, out of the length of the hash map.
What is the length of the hash map?
The total size of the hash map.
What is that?
The total size of the hash map.
What is that?
So every 2 pairs n square.
Mm-hmm. That's also n square?
That's also n square. And then you go through the values and then you find the respective keys.
And it's not just n square, because as you go through the n square, whenever you have like a collision, you are actually trying to go look at the keys to make sure that you're not messing things up. So there is some constant here. Usually I think it's usually 2 or 3 collisions might be there, right? You may want to inspect the keys. You want to verify the keys are unique.
Oh, I see. So the collisions you'll not add in. Okay.
You want to make sure that you want to eliminate those things, right? So there's some factor here, and what that factor is. But in typical, this is essentially an n square solution, which is actually better than
n cube.
Than the n cube solution for 4-sum. But it's a lot more complicated to write.
How do you guarantee that the same number is not being used again? Like say if you have 3 ones, so
this example, right? 85, 86. So if with 1, 2, 3, 4, 5, and I want you to find 17, with this hash map solution, you will say that it exists because you will pick 3 plus 5, which is 8, and you will pick 4 plus 5, which is 9, and you say that this is total 17. So yes, I found an answer. You would say that, correct? Right? That's the challenge that's the risk that you run into. So here, when we did this, we will actually say that this is 2, 4 is what you will put in, saying that the keys that went into making 3 plus 5 actually is 2, 4. The keys that went into making this is essentially 2, 3, 2, 4 and 2, 3, 3, 4. Right? That's what went into making this. So once you have found the answer, you will go and make sure that all these 4 keys are unique. Rather, nothing of this key belongs to that key, nothing of that belongs here. You just have to verify that.
Okay.
So the keys are basically the index in the array, right?
The keys are indexes in the array, that's correct. So this is a set of 2. And this is a set of 2 also. Right? You're just making sure that nothing from this set of 2 is in the set of 2. So this factor is essentially 2 in that case. Because every time you have a collision, you will actually go and inspect if all the keys that I have for set 1 is actually there in this. And this is essentially k, not really 2, because in this case, k by 2, right? In this case, it's 2-sum. It's 4-sum, so it's k by 2 in this example. So far with me?
Yeah.
One query here, Vivek.
Go ahead.
We did the hash set for 2-sum and 4-sum. Do you think it can be used for a 3-sum as well?
Aha, that was the next question. So fantastic. So I went to 4 because it was much easier to do it this way. For 3-sum, what you can do, let's do 3-sum, right? So you have 2 options here. Either you can create a set which contains the n, okay, or you can create a set which contains the n square. Okay?
Right.
You could do that. And then, what is the lookup complexity?
Constant? Because
Not constant. So this contains, essentially this will give you a set which contains a comma b, essentially all combinations of a, b. Now to find c, you have to iterate over the entire array.
Right.
And then you have to find its complement in the n square hash map.
Right.
Yes.
Correct?
And then once I find the complement, I have to look for
and then you have to make sure that the keys that went into making that element in the hash map is not the set, right? Does not contain the current index that current index c is not equal to a and c not equal to b. You have to verify that. That will be a simple like a set lookup, right? It will be a hash map with a set lookup, and that's like n times 1 only.
Okay.
Right? So this is an n square solution, which is the same as a sorting solution. Right? So sorting solution is n square
space.
with extra. Well, this one uses n square extra space. Sorting uses O of n extra space technically, because even though you are actually destroying the array, it is considered like you're just reusing the array space. It's still considered use of space, right? Technically, it's of n space, the sorting solution. But if you're doing in-place sort and you're okay to do that, then you're looking the other way, then you're fine with that. Okay. So let's do 6 sum just for giggles and see how that goes. How do you think 6 sum will work? Let's do the Hashmap technique. The sorting technique is simple. It's essentially n power 5. That's simple. Okay. Hashmap technique.
So you can do like 3 and 3, like IJK and
yep, LMN or
ABC.
LMN. Yep, or
yeah,
ABC, DEF. So that's n power 3. You got ABC in it.
Right, and then in part 3, you would get another element.
You can find the DEF with this. So essentially, you're using the same thing, going through the entire list. And the thing you're trying to do is that when you're doing this, you also need to make sure that neither D nor E nor F is actually in the ABC set.
As a key, right?
So that's essentially times 3. Not always. Anytime you find a match where your solution exists, like just like
so
how you saw 17.
Oh, I see. So first of all, you do the n cube ABC things in the hash set, and then
This
the
is
next
to load.
Right. So the first thing is to load, and the second thing is to like look up for the match. So the second time when you look for the match, you need to make sure that D is not equal to any of the ABC.
Correct.
And E is not
E
equal
to any of ABC.
So that's times 3. Yeah.
So when you load, you actually load this in a set, right? The key is the sum of A of whatever, like array of A plus array of B plus array of C.
Right.
And the value is essentially a set which contains A, B, C.
Right.
And then when you do the lookup, you're actually looking up array of D. You're basically what you're looking up is like you're looking up the Hashmap key.
Right. That has the value which is like less than the target.
Yeah. Correct.
Complement of the target.
Complement of the target, and then you're just making sure that the value of the hash map that you have, that you currently are looking up, that is the DEF.
Right.
Right. That's the DEF. And you're checking that D is not D is not in ABC, E is not in ABC, and F is not in ABC, and we're done.
Perfect.
And right, so what's the time complexity of this operation? It's actually
n cube plus
n cube plus n cube times 3, which is essentially n cube as well.
Right.
Right. So this essentially scales pretty well, and you can mathematically look up the actual thing. Is essentially it is n power k divided by 2, and you're just up rounding it. Right.
So what if k is odd?
Yeah, up round it, because we just did that, right? For 3 sum, it's still 2. So if you have like 100 sum, you will be able to solve it in n power 15. If you have 105 sum, then you will need n power 53. Sorry, 53. 106 sum is also 53. The reason why is that it's actually n power 53 plus n power 52 in this case, and in this case it's n power 53 plus n power 53. That's why. One is to load, and the other one is to look it up. So I know so one of the challenges with this format and the time the paucity of time that we have is, unfortunately, we'll not be able to go through the code for these things, but the code for this should be fairly super simple once you understand the logic behind it. There is quite a lot of value in actually writing this down, especially the Hashmap technique for k-sum, right? And writing arbitrary degrees of k-sum is actually pretty hard. The reason why it's hard is that you guys know how to write a nested loop, right? You know how to write a nested loop of 2. You know how to write a nested loop of 3. But how do you write a nested loop of k or k by 2? How do you write a nested loop of an arbitrary number? Like, and that's not, it's not something that is very obvious and logical. So think about it. Think about how you want to do that, and write code. So that part, I think I'm going to leave it out. And I want to switch to the next question. Any questions before I jump on to the next question? Make sense?
Yeah.
All right.
Yeah.
Going once, going twice, and done. Go ahead, Tian. Do you have a question?
No, I say yes.
All right. Fantastic. No worries. Got it. So let's move to the next one, right? So this is good. I think we went through all the combinations and we did that. Now let's do this similar thing, but except that you're given a bunch of integers, and your goal is to actually find the maximum product, like of two numbers. What would be the how do you find out which two numbers can multiply to? And this is an unordered set. So you got like 1, 3, like 2, 9, and like 5 or 4, right? So what do you think is the largest product that's possible? It's 36 in this example, right?
Is there any like negative in the array?
Fantastic question. I said unordered integers. So yes, negative is possible. So let's assume that there's a -3 as well, right?
Cool.
The answer doesn't change. It's still 36, correct?
Right.
So one way to do this, which is again going back to the brute force, is essentially doing n squared, where you look at every combination of numbers and figure out whether it is whether you can the multiplication makes sense or not. It kind of works. What is an alternative? Can you do better than that?
I think the entire array can be traversed once to find out the maximum and second maximum element, and also minimum and like second minimum.
We'll get to that in a second. So the reason why you want to do maximum and second maximum is because, well, the product of the top two numbers is going to be the answer. Except when you have negative numbers. Like what if I had a -10 and a -5 or something like that, right? The top two numbers are 9 and 4, that's 36. The bottom two numbers are 10 and -5, that's 50. So multiplication actually, since two negative numbers yield a positive, so you traverse once and you get both, the max and the second max, the min and the second min. And what are you checking, Jaspreet?
So basically, you can multiply the max and second max, and then you can find the product of min and second min and compare both of them to figure out which one is greater.
And then you're done, right? So you're just comparing. So what is the time complexity of this operation?
That would be O of n, because you're traversing the entire array just one and then maintaining 4 variables. So the space complexity would also be O of 1 because like it's constant space.
What is the can you be a little tighter even with constants?
So basically you just have 4 variables. So it would be O of 4. I mean, if you consider one variable to be, so that would be O of 1
so
basically.
It's n times because you're going through the whole items. You're keeping 4 variables, but you're keeping 2 sets of 2 variables, right? And then you're actually shuffling them around based on comparisons, right?
Oh, you wanted me to be tighter around the space, time complexity. I was trying to figure out the space. Okay, yes.
Time complexity. So if you actually had a heap, right, of size k, then it will be log k. So in this case, the size is 2, right? Finding the top 2 elements is essentially, this is just a constant, anyways. So it's O of n. From your algorithm is O of n, but given that you're keeping 2 heaps to find the max and the second max number, that actually works out as log k, right? Log 2. So follow with me?
Right.
Just if you're not with me for this one, that's okay. So that's how product works. Anybody has any questions on why max product is? Why do you want to do minimum maximum to get this?
No.
So here,
I don't understand the log of 2.
Oh, the log of 2 is. Let me walk through it one more time. So that essentially the way you find the top k numbers in an array using a heap would essentially be n log k, right? Have you used a heap to figure out the top k elements in an array?
Yes,
That will be n log k, correct?
that's correct. Yeah.
Yeah. So in this particular case, you're looking at a heap of 2.
Oh, okay, got it.
So that's why it's n log 2 in this case, and log 2 is constant, so you can actually ignore that. Okay.
Okay.
So that makes sense. But if I were your interviewer for this particular question, I will not accept the solution. Why? Like, I can easily see an interviewer actually stump you with this question a little bit. Why?
You not like it because of the runtime complexity, or because of could potentially produce error?
So tell me what's the maximum product of this element, this array?
Okay, there can be an overflow.
Absolutely. Any integer problem that you look at, immediately jump to the overflow. Like, have an eye out for overflows, maximums, wraparounds. I mean, those things have to be in your thought process. Even in the n-sum problem, two-sum problem, when we talked about it, we didn't talk about wraparounds and overflows. The same concept applies here as well, right? So it's possible. The answer is very clear. It is definitely the last 2 elements in this case. But you cannot do that because you cannot multiply. All that is guaranteed is all the elements in the array are actually in range. There is no guarantee that the arrays or the elements are actually, when multiplied, will be in range. But that does not mean the product is not the maximum, right? So how would you solve this?
I'm not sure if it would be 100% correct thing, but I'm just thinking if instead of taking the product as an integer value, if we take it as a long int or something like that.
Floating point?
Yeah, floating point.
No, please don't do that. Please don't. So
not floating point though, but long int or big int or something sort of
else.
Integer.
Use a different data element or data structure or data type that actually has a bigger storage space so that you can actually make this work. Kind of works. You can use things like a big decimal or big number. There are like different data types in many languages which let you store arbitrary length values, and they're slower, but it actually gets the job done. May not be the right solve, but it's like you're only doing one comparison, so it's not really that expensive. So you're probably okay with that. The other way to also look at it is that there should be a simpler way for you to find out if the numbers are like what if there are no 2 negative numbers, only one of them is negative, the other one is not, then you know that the answer is the top 2 anyways. So there are like a few conditions based on which you can eliminate that, right? And the other thing, of course, is that you can also eliminate conditions based on division instead of this. You could be looking at A by B, or like A, B, C, D are the 4 values that is given to you, and you're trying to figure out if A times B is actually less than or greater than C times D. That's what you're trying to find out. You could essentially find out A by C, is it the same as D by B, and you could use different mechanisms to figure out which one's closer, which one's not, and things like that.
Cool.
Okay, so there are other techniques. Essentially, what you will do is that you will have reminders. So this won't be a perfect division, right? A by C will not be a perfect division. So you will essentially express this as X by C plus something from some constant. This will be like a common number plus like the division, and then you will actually check this is Y by B, and then plus some other number. So you can math it out and figure out if this actually is working or not.
Okay. I thought we only do comparison. We don't multiply them in our algorithm, right? We just compare each element and get the top 2 or the bottom 2.
So that is correct. That is not the challenge. Once you have done that, how do you figure out whether your answer is the multiplication of the top 2 or the multiplication of the bottom 2?
Okay.
Once you have found out A, B, C, and D, where A is the smallest number, B is the second smallest number, C is the second largest number, and D is the largest number. You found A, B, C, D. Now you need to find out if A times B is less than 3 times D or A times B is greater than 3 times D or equal.
The absolute value of the numbers and just compare the numbers.
That won't give you let's forget the negatives at this point of time, right? How do you actually make sure that A times B is actually less than or greater than 3 times D? Just comparing A and C and B and D is not enough, right?
But wouldn't that the top two, if it's no negative number, the top two would be the answer, right?
If there are no negative numbers, but so what you have found is you have found A, which is the smallest number, and you have B, which is the second smallest number. Okay. Now, if A and B signs are different, then the answer is essentially C times D, no questions. Okay. If A and B are both negative numbers, then you don't know whether A times B is less than C times D or greater than C times D. Just comparing A and C or B and D is not going to be enough.
Okay, got it.
Right? You need a little bit more math around it. Okay? So again, my whole point of this discussion was more in terms of trying to introduce the concept of the stupid overflow can happen anytime. So please make sure that you're always thinking about overflows whenever there's any mathematical operation that's being performed on these things.
Okay.
Okay. All right. Moving on to the next variation of this, like what about 3 products, like product of 3 numbers? How would you solve for that? Would that just be the top 3?
Max 3. Max.
Yeah,
3.
max 3.
And then 3 elements, limited to 3 elements, and make it single run.
So you will find the 3 smallest. Hang on, let me just walk through this. You find 3 smallest and D, E, F 3 largest. Is that what I'm hearing?
I think it can definitely, one possibility is 3 largest, and the second possibility can be 2 smallest and the largest. Because
correct.
If you are considering 3 smallest, if they are all negative, then definitely the result will be like negative, which cannot be the greatest product. And in case if there are 2 negatives and 1 positive, I mean in any case, 3 smallest would not give you a maximum product.
Yeah, 3 smallest will give you a negative number at best. So they are like gigantic negative numbers. Or even if one of them happens to be positive, it will be a tiny number. So it doesn't make sense. So it's essentially A, B, and F, more or less.
Mm-hmm.
Right? Where A is the smallest, B is the second smallest, and F is the largest.
The largest.
And then D, E, F is essentially where D is the third largest, E is the second largest, and F is the largest, and you're done, right? So that might be the case. So let's do like say 10 product. How about 10 product? So I have A, B, C, D, and E as the 5 smallest ones. F, G, H, I, and J as the 5 largest ones, just for giggles, okay? These are the largest ones. So how does it work?
It can be so the largest ones, F, G, H, I, J, can be one solution. If not, then A, B, and J, and A, C, and J, A, D, and J.
Gets more confusing later, right? So you could essentially have a scenario of where it's just all positive numbers, or it's like 2 of the negative numbers, which is the bottom 2, and it's 3 of the positive numbers, right? Or it could be 4 of the negative numbers and 2 of the 1 of the positive number.
Do you mean to say that this is a 5 product question, right? Not a 10 product?
It is a 10 product question. So sorry. Then let me actually write it that way. It's 2 and 8. It's more. Thank you for that. And 6, or it's 6 negative numbers and 4 positive numbers,
8.
or 8 negative numbers and 2 positive numbers, or 10 negative numbers and 0 positive numbers. So it's any of this.
Or just 10 positive numbers.
Yeah, that's the first one.
Oh, okay.
Right?
0, negative, 10 positive.
Yeah. So that's all the possible combinations.
10 negative numbers, because 10 negative will become negative. No.
Right. No, 10 negative will be positive.
Okay.
Right? So what you will do is that you'll essentially identify the 10 most negative numbers and the 10 most positive numbers, and then you will generate these 5 combinations of numbers, and then you'll just figure out which of these 5 combinations is the best, and you're good to go. Right?
Right.
What's the big O of this operation?
So I think again, if you want to take the 10 positive or 10 negative, you can again use a heap for that.
Mm-hmm. So log K.
So it will be right, and then you might just want to traverse the array once.
Mm-hmm.
So it should still be.
Would that be it? You get like 5 combinations, 1, 2, 3, 4, 5, 6 combinations essentially.
Hello?
Yeah, go ahead, Ivan.
Hello. So, like, are you able to see the screen?
Folks are able to see the screen. Yeah,
Like-
folks, are you able to see the screen?
Yeah, I can.
So, I can't see the screen, so, but I'm able to hear you, hear your voice, so...
So what you can do is go to the wall, and you should see a link which actually says shared scratchpad, Etherpad Mozilla. You can go click on the link. It will bring you to the Etherpad. I am actually discussing this and typing this in the shared Etherpad. I am at line number 141, so you should be able to scroll along on the Etherpad as well. If you don't have to see the screen per se.
Okay, so are you saying, we don't, are you saying we're not gonna, share the screen for this time, right?
I am sharing the screen, but if you're not able to see the screen, then go to the Etherpad and then follow along in the Etherpad, because I'm typing this in a shared screen. So you don't have to necessarily view what I'm projecting, but you should be able to view what I am typing in. So just go to the Etherpad link that is there in the wall, and you should be able to see it. The SBA skills wall, in the meeting resources, the very first link on the top is the Etherpad.
Oh.
Click on that. What I'm typing is actually in line number 141.
Oh yeah, I'm changing to internet, so internet.
Okay. All right. Are you able to see the screen?
I'm seeing the screen.
Fantastic. All right. Good luck. Good. So let's continue. So in this particular case, I am actually seeing the time complexity is n times, because you're actually going through n. The log k plus log k, because you're actually finding the smallest k by 2, right? Not k. Just to be tighter. And you're also trying to go through, essentially you're going through 6 combinations if you want to get to log 10. So essentially this is this plus 1, I think. Right?
Right.
So this works, and again this does suffer from the problem that you have, which is essentially how do you deal with the negative, positive, and how do you actually do the comparison? You can't multiply 10 numbers and expect that to be within range.
Right.
So you need to find a way to compare, like, A times B times C times D times E with, or whatever, up to 10 numbers, and then on the other side also you have 10 numbers. You just have to find a better way of keeping that going. So let me actually ask you maybe a different question, right? So let's assume that you have the max product function available, which actually takes an array of n numbers, and it takes a k as input. Okay, so we know how to solve it for k equals 2, right?
Mm-hmm.
So imagine you also had a min product function available. Okay, which does the same thing. Okay, now the fun thing here is that your max product for n numbers with 10 elements, is that the same as max product of essentially 8 elements with n minus 2 elements? From 0 dot dot n minus 2, and it's the max product of, again, n minus 2 elements, but this time you're actually going from 2 dot dot n, right? Is that not so?
So n and k, as in like n is the number of elements in the array, and the k is the
product
of
size,
the
yeah.
element.
Because the max product of this times a of 0 and times a of 1. That's what this is, and this one is a of n and a of n minus 1, essentially. So you're just writing a recursive function to do the same thing.
Right.
Right? So this gets you for our even numbers. Doesn't get you for odd numbers yet. Right? So then you need to do min product of n minus 1 of 9 and times a of 0 and min product of n minus 1 and 9 times a of n. Right? These are the 4 that we probably need.
Vivek, do you mind explaining these again?
This is a recursive way of defining the same thing, right? So let's assume that you have a max product and min product function defined. Okay?
Right.
So when k equals 1, right, the max product is what? Is a of n minus 1 basically, last element is max, and the min is what? A of 0.
Right.
Okay? That's defined. Now, what you're saying is that if you want to find max product of this, actually you don't need to do this, right? You can just kick this out and that's it. It's just this.
Max product of is equal. So max product of n with 10 elements is equal to
so max.
min
So
product.
you're trying to find the minimum product of the 9 numbers to my right. Actually, no, sorry. So this is max. This is if a of 0 is negative, else ignore it. Would that not be so?
Yeah. Yeah, I understand it now.
So if you're this is just a recursive way of thinking about this question. That's all. So max product of n comma k. Let's actually do it k. So if you want to find the maximum product of k numbers, then you look at a of 0, the lowest number, right? If a of 0 is already positive, then there's no point in looking at it.
Right. So we can just go to the other arc. Right.
Then you just look at the max product. So essentially, then the max product would be of all the n minus 1 elements, k minus 1. So all the elements from 0 dot dot n minus 2 essentially multiplied by a of n minus 1. That's all. That's the max you can do.
Yes.
Okay. But if a of 0 is negative, then you can take a of 0 and then identify the min product of the 9 elements, which is essentially starting from 1 dot dot n minus 1. Correct?
Okay.
In the same way, you can define the min product of n comma k as what? It is
The opposite max product of.
It is essentially min product of, this is like, it's exactly the mirror image of that. So if a of n minus 1 is positive, then you can actually check the min product of all the numbers from 0 dot dot n minus 2 comma k minus 1 multiplied by a of n minus 1, because this is the positive number. The negative number, minimum negative number, like the most negative number on the left, and multiplied by the largest number will get you this. And it is essentially max product of 1 dot dot n minus 1 comma k minus 1 times a of 0.
Okay.
It will be the minimum of these two. Right?
Okay.
This is a different way of thinking about it.
Okay.
Any questions? Just you
I'm
had
a bit
originally
lost
had some
on the
questions.
second part yet. I'm just thinking, I mean, for the min product, I understand that you check the last element. If that's positive, you're taking the product of the first k minus 1 elements and then multiplying it with the last element. That's fine. I'm still trying to understand the second part of it.
It's the same as the previous setup, right? So what you're doing is that I think I made a mistake, right? So this will be essentially you want to find the min product of a of 0 is negative, right? Typically you expect a of 0 to be negative. Okay. So you want to find the maximum product of the remaining numbers, and then you multiply to the a of 0, assuming a of 0 is negative.
But then there can be one more condition here, right? I mean, if a of 0 is negative, then you go ahead with this. If it is not negative, then you find the minimum product of
no, it's not. It's not worth it. It's the same thing with here also. In 150, the same thing, right? What if a of n minus 1 is positive? A of n minus 1 is not positive. It's what if that is negative? Actually, I can just say that if a of n minus 1 is positive, else ignore. Right? Both conditions cannot be true at the same time.
Right.
Right? So I can say that the same. So I can do that here as well. So I can do if a of 0 is negative, then do this. Both conditions cannot be true at the same time. One of the conditions will definitely be matching.
Right.
Right. So this is just the concept here is that trying to make you think recursively how this actually works. I mean, it's like trying to evolve a max product question from a 2 product to a 3 product, 4 product. I mean, how do we go through this thought process of actually starting from a 2 product, then 3 products, and then we do a bunch of different things, and then we get to this. Now, the fun part of it is that at this point of time, right, you are what you get back is again overflow is still an issue. You still have to deal with that. So that is like a separate conversation. So any challenges so far?
No, I still have to take this down and think through it.
Absolutely. Absolutely, Santosh. So do think about it. See how you can write it. For now, you can make assumptions that the multiplication will not overflow. Right? Just use that because the multiplication overflowing is like a bigger mess. So then you can solve this question pretty quickly. There's a very, very easy solution. A recursive solve, given that you know how to solve it. When k is 1, then you just return the a of 0, and when k is this, then you return the a of max, and you're just done. It's like a very quick solution.
Okay.
Right?
Yep.
Awesome. And this actually works for this will also work for k equals 2, right? That's the easy case for you.
Yeah.
Okay. All right. So that is awesome. This is assuming it's sorted. So sorting is an n-log n complexity on top of it, but this is just a different. I mean, you can do it without sorting because you're always only looking for the largest and the smallest numbers, so you don't need to sort it, but you'll get to what you need to. Okay.
Yeah.
All right. So switching on to the final question of the day, which is max XOR. So this one is super tricky. If you haven't done it before, you will actually we'll be thinking about it. So let me stop and ask, how many of you have actually seen the max XOR question before? Like, have you seen it?
I've seen the question on the Slack channel, but not the answer, or I haven't thought about that.
Yeah,
I posted it. I posted it in Slack at some point. So yeah, how do you think? How do you do the XOR? What is XOR, and how do you find out the max XOR? Let's assume that you knew nothing. What's the easiest answer for you?
If the bits of both the numbers are totally opposite, you get the maximum.
Well, that's
XOR.
like, yes, but that's a very special case, right? Let's assume that you didn't know you didn't know any clever tricks or anything, and I asked you to find the maximum XOR between any two numbers. How will you find out? Brute force. What's a brute force?
Go to all pairs and get a max.
Exactly. Find all pairs of numbers, do the XOR, figure out which one's maximum, right? That's a very simple n-square technique, which is identical to the twosome problem. Correct?
Right.
In twosome, you just did A plus B. Here you're doing A XOR B. That's it. No big deal. Correct?
Right.
Okay. Now comes the clever part. How can you be cleverer? So in the twosome part, what did you do? Was that you wanted to actually, for all elements, okay, you wanted to find if it's like complement is that, right? That's what you're trying to do in the map. That's kind of what you're trying to find out, correct? Map or set or whatever that was. So here, what you're trying to do is that for every element A of I would like to find the best number in the array that actually, when XOR'd, gives me the largest value. What would be the best value for any number? Which number, when XOR'd with something, will give you the largest value?
0.
Negate that number and look into the array.
Is it 0?
Is it 0? Forget the array at this point of time, right? If I give you a number, like say, if I give you like 45, right? What is the number that you want to XOR with 45 that will give you the best 16-bit number, or like 64-bit number?
Oh, it's the 44. The 1 minus 1. N minus 1 will give you the maximum XOR. Okay.
Are you sure?
No, it just remove the last bit.
44 will just give you the last bit, right? Let's assume I did 15, sorry. Then you did 14. If you do XOR of 14 and 15, it's just 1, 0, 0, 0, 0, 1. That's it. Correct?
If it is for the powers of 2, then it would, yeah.
If that's okay. You're getting there. You're getting warmer, but that's not necessarily the right answer. Let's assume it's 16, right? 16 is what? Is 1,000? One more? 10,000?
Right.
No, 4 numbers.
16. Yeah, 4.
1, 2.
Yeah, 3.
4, 8, right? So 8 is 16. So there's one more 0. This is 16.
If you make 15, then it's like 0 is the right opposite.
So it's 1, 1, 1, 1. 15 is 4 ones, right?
Right. And you make an XOR, you get the max. Right?
No, you don't get the max. What do you get? You get 31. Right? 31 is not the largest 16-bit number.
Okay.
If you XOR this with 32, for example, you actually get 48. Is it not? Which is bigger than 31.
Okay, I see. I see the point. So you're asking for the entire 32 bits.
In a 64-bit number, what is the best friend for any number?
You said it's complement?
It's its complement, exactly. Because X XOR X complement is what? 1, 1, 1, 1, 1, 1, 1, 64 times. Right?
Yeah.
That's correct, right?
Yeah.
Okay. So let's assume that you are looking for, so 64-bit is too big. So let's actually do 8-bit numbers in this case, right? For simplicity, because I just don't want to put that many zeros. Okay. So let's assume that I have 127 as my number, which is essentially 8 ones, 7, 0 and 8 1, 7 ones, 3, 4, 5, 6, 7. So this is this, right? So the best number that I can XOR this with is 128. Correct? 4, 5, 6, 7. Right? Is that not so?
Right, that's the max XOR.
That's the best I can do, right? Now, now let's assume that. So let me actually just for this, let me just make some tweaks here. I'll put a 0 here. I'll put a 0 here. Okay. That means I'll just have to go to the corresponding elements here, and then put a 1 and put a 1. Right? If I did this, this is not x. Correct?
Right.
This would give me the perfect number, which is essentially 1, 1, 1, 1, 1, 1, 1, 1, 1. That's the largest number as possible, max XOR, right? Now let's assume that this guy, this not x was not in my array. Then what would I prefer?
Then can you take the int max and then do?
No, not it. So let's assume that I had a very similar number available, but with 1 bit off. Okay.
You just do -1 to it.
Let's assume there's just 1 bit off. That's okay. And I have another one where this bit is off, but not that bit. Which one would you prefer? This is A, and this is B. Right?
B. Prefer B, right?
Would you prefer B or would you prefer A?
B, because you would want the most significant bit to be 1 in the final answer. Okay, so
no. Hang on. So X XOR A is what? Is 1 0 1 1 1 1 1 1 1 1 and then 0. X XOR B is 1 0 1 1 1 1 1 1 1, right?
How is 0?
Because X, what is X? Let me paste X right next to A and let me paste X at B. If the elements are same, then it will become 0, right? So X XOR B should be 1 0.
Yeah.
X XOR A is like 1 1 1 1 1. Final thing is 0, right?
Yeah.
Which one do you prefer?
XOR
The
prefer
A.
Anyone?
The first
A or B. XOR A. Sorry.
A is better, right?
A is better.
A is better. So you want, if at all you have a mismatch, you want the mismatch to be as much later in the game as possible.
Yeah.
Perfect.
Sorry, maybe I'm missing. XOR is either of them is 1, then you get a 1, or both are 1 also you get a 1, right?
No. XOR is exclusive OR, which means either A or B, not both. XOR is exclusively OR. So exclusive OR. So 1 1 is actually 0. 0 0 is 0. 1 1 is also 0. 0 1 is 1 and 1 0 is 1.
Okay. All right.
Okay. Well, without that fundamental clarification, I don't think you'll be able to solve the rest of the question. So that will help. But
so it's basically like the next greater number after complement of x is right shift the x.
Don't right shift yet, but I think start with this, right? So what you want to do is, for you, the best number that you can actually find is the number. Let's assume this was x, right?
Mm-hmm.
I would like to find all numbers that are actually beginning with 1.
Right.
Any number that is XORed with something that's beginning with 1, 1, 2, 3, 4, 5, 6, 7 is definitely better than any number that is 0, 1, 2, 3, 4, 5, 6, 7. Correct?
Yes.
Mm-hmm. Yeah.
So far with me?
Yes.
If you find even one number that begins with 1, you can ignore the entire 0 set. You don't care about any number that begins with 0.
Right.
If there is no number that begins with 1, then you don't have a choice, but you have to, okay, you know what, let me find out which number begins with 0 and continue. Correct?
Right. And then find the next bit 1.
Then ignore the first bit. Now, then for the second bit, what you're trying to do is I need to find all the numbers that begin with 0. So 0 followed by 7 question marks is better than 1 followed by 7 question marks. Like, A belongs in this category and B belongs in this category. So A is preferred.
I didn't get this part. Right. So the first bit is 1. If the first bit is 1.
You figured the first bit, right? So you solve the first bit.
Right.
So first bit is 1. So you know that.
So I go with the A. Right. So
in this case, the second bit, you prefer the ones with a 0 as opposed to this, because the second bit of x is actually 1, so which means you want to find not 1.
Right.
If nothing in your array actually has is 1 0 something, then you don't have a choice but to pick 1 1 something.
Perfect.
Correct?
Yes.
Okay, and so on and so on, and you need to do that. Now tell me, what data structure will you actually use to store this information? Like, how would you compile this information and how would you traverse this? What data structure will help you figure out if there is any number that actually begins with 0 and any number that begins with 1?
Tree?
Yeah.
Trees.
Yes.
How trees? Not just any tree.
Prefix tree.
It's a prefix tree, right?
Right. Yeah.
Sort of a trie, but it's a binary trie of sorts, right? So what you're doing is that you're actually trying to you take your number and then you insert it bitwise. So essentially, you insert base. The first bit is the root element, or like the first bit is the first level. So this is the root, which is nothing. Then you have this is based on the first bit. Then this will have a 0 and a 1, and this will also have a 0 and a 1, and so on. So given an 8-bit tree, how many elements? So how many? What would be the depth of this tree? 8, right? 8. Given a 64-bit, what will be the depth of the tree? It will be 64. And depending on the number of elements that you actually put in there, how many leaf nodes will exist?
2 raised to n.
N by 2?
No, why n by 2? It will be n. Every leaf node actually represents, like, you traverse from the leaf node all the way to the root, you get the number itself, right?
Yeah.
So you should have n elements. There should be n leaf nodes. I mean, assuming they're all unique. Right?
Right, that's fine. That's fair.
Got it? So now, as you are assembling this thing, you can just go build a prefix tree based on that. Right? This
So
bit,
for
bit tree. You make this bit tree, and then for every number that you have, so what is the time complexity of building this bit tree?
For every element, you have to go down the tree. That's like n bits.
So essentially,
so it's like n times n.
It's not n bits. The bits are actually k, not n.
Yeah, because it's 64 or 32. Yeah.
No, but and k is actually, what is k?
The longest.
K is the number of bits in that number system, right? Correct. So if n is like n is pretty large, then what is k? K is actually equals to log n. If you have 8-bit numbers, the most number of numbers you can actually have is 256.
Yes.
Because it's 2 power k, right? If the depth is k, the number of n's that you can have is 2 power k. So essentially log to the base 2. So k is equals k is log n. So technically the cost of inserting this is n log n. Okay? Sorry, I put 2 n's. Okay? With me so far?
Oh, I see. So you just replace the k bits to log n. So
that is correct, right? Because k is log n. Okay.
Yeah.
And then what is the complexity of actually going through each element in the array, that's n, and then finding its best friend in the tree?
So that's like
the finding the best friend is also k.
K, right? So it's log n.
Yep. So it's n log n plus n log n, which is essentially again n log n constant, right? So you should be able to traverse this thing in n log n time using this prefix tree. This is ultra complicated in terms of, like, I don't know how people will be expected to arrive at this, but but it is a structure nonetheless. Now here comes the interesting part. Okay, how would you actually find out min XOR? We did max XOR, right? How do you find min XOR?
Minimum is the same element. Right?
Build a suffix try instead of a prefix try.
No, that suffix wouldn't make a difference,
No.
right? You still need prefix.
The min XOR is like, if I do the XOR of 1 and 1, then it will be 0, right?
Correct. So the definition of the best friend changes, that's all.
Right.
So I just
try
find
to
the identical element.
You want to find the
Only
element
the
that is closest to me
right.
from the left.
Right.
The rightest bit is and the rightmost bit is different than the minimum XOR.
No, you should still start from the leftmost. You should still start from the leftmost. In the max,
Right? You look for the same number.
correct. In the max XOR, you were looking for its complement. So you were trying to figure out who is closest to my complement. Right? That's how you're doing XOR. In the min XOR, you're trying to find out who's closest to me.
Yeah, okay.
Right? So if it's 1, then you go down the 1 path of the tree. If it's 0, then you go down the 0 path of the tree. This will not work in the algorithm that we talked about. Why? Max XOR has an advantage because the element, max XOR, it's never, X XOR X is never an answer for max XOR, right? So duplicate elements is not an issue for max XOR. The way we did the tree, right? What we did was we said in line 221 we are saying we will use n log n pass to go insert all the numbers in the tree, and then in another n log n pass we will go and find the best friend, right? That's what we tried. Unfortunately that won't work because you will find the best friend of every number now because that number is already in the try, no? In this tree, not try. So how do you compensate for that? So do you understand the question?
I kind of. Can you repeat it again, please?
Yeah. No, if I put numbers like say 1, 2, 3, 4, and 80 in the tree, right? I'm trying to find out the best number that will give me the min XOR. I think the min XOR answer is probably 1 and 2. No, actually not 1 and 2. It's actually 3 and 2. 3 XOR 2 will give me 1. That's the lowest answer in this case, correct?
Yeah.
All other numbers will fail. But unfortunately, what did you do is that you inserted all the numbers in the tree, right? So you will find an answer which is essentially, if you want to find the best friend of 1, you will actually find it because 1 is also there in the tree.
Yeah, so you're not supposed to take the same element.
How do you know that? And how will you figure it out? And what if 1 was there twice? Then you should take it.
Okay, I see.
So how do you know that you should or you should not take it? So that max XOR doesn't have that problem because duplicate elements is irrelevant. Min XOR, that's the problem.
Max XOR is irrelevant because you're finding the complement.
You're finding the complement, and I mean, if the only reason where it will fail is that you're looking at max XOR of just one element, which is like insufficient data. That's like a very simple check for you to do. If you only have 2 elements, then you will find max XOR of both elements, and that will be the answer. It will never be that, right? The numbers are the same, then that's the same answer anyways.
So in this case, like in the try, in the leaf node, you can just make a count kind of a thing, for like 2 or something. So in this case, like 1, 1, 2, 3, 4, 18. If I make a try, I have a 1 path. In the leaf node, I just make a comma 2 in the leaf. So once I see the 1 again, I traverse to the depth. And if I see the leaf node with 2.
Why not? But do you think you'll find a better answer than that? At the point you made it 2, you know that there are 2 80s, right?
2 ones. Yeah.
Just return it. That's it. That's the answer.
Oh,
moment, as a part of constructing of the tree, if you find that you have already seen that element before, like you've gone through the entire tree and you've seen that element 80 is already inserted once and you're trying to insert it again, you know that that is like 80 XOR 80 will be 0. There is no better answer that you can get.
Oh, I see. Okay. So
Right?
instead of like going through the other n-log n, you can just finish it off in the first n-log n.
Exactly. Right? So that is one way of doing it.
Okay, cool. Yeah.
Okay, the second way of doing it is that you actually find its best friend right off the bat and then you insert it. Just like, remember the hash map that Ankur's technique where he talked about you check first and then you insert? You can do the same thing here as well.
So first of all, you do the
best friend in the tree. Whatever the tree you have, just do the best friend of it first. And then if you don't, whatever the answer is, keep it aside and then you insert this number.
So what if the best friend doesn't actually exist in the array?
It will always exist, right? But not the best friend as in the closest best friend is what you're always finding. So what you're trying to do in this case, but the XOR is symmetric, right? So if you know that 40 XOR 96 is that final answer, when you inserted 40, at that time you wouldn't find 96. The best friend of 40 will be all the numbers to the left of 40. You'll find some best friend based on that. And then when it comes to 96, you will find that 40 is the best friend of that. It will still work. So you can actually check and then insert. These are two different techniques. I mean, I think there is no, the best way of doing it will essentially be as you insert, if you find a duplicate, then just insert it. Then return 0. That's the best answer. But but if you wanted to apply the same technique as you said before, then you could do that too.
Okay, cool.
Does that make sense? I mean, the goal of this is not to solve this one problem. I mean, this is not how you practice, right? The whole idea is not to learn how to solve this question. It's all about like trying to internalize different techniques and tools so that you can take these techniques and apply it to other questions that you see.
Okay. Yeah.
Right?
That's the best.
Yeah. So that's what we're trying to do. So any questions? I think Jaspir, you're not convinced.
I think I'll take some time to look at this result.
Yeah. So in this particular scenario, what you'll do is think about the solution that I'm proposing is essentially two solutions here for min XOR. Number one is essentially
the first one that you proposed, that just in case, like while writing.
If it's duplicate, just do it.
Yeah,
that's easy. The second scenario is basically what you're saying is that in your min XOR, what you're trying to do is that for every number, right? You're trying to find the min XOR. You're trying to compare it with all the numbers to its left. You're trying to find the best number when you XOR with elements to its left that will yield the minimum result. That's all you're trying to do.
Oh, okay.
So, which means because you're building a tree only with the numbers to the left of it so far, right?
Right.
You built a tree with 1, you built a tree with 2, you built a tree with, that's it, that's all you've done. When you're trying to process 3, you only built tree with 1 and 2. Let me remove this, okay? Then, once you're done that, once you've found the best way of handling between 3 and this, you found that it's actually 3 and 2, that's fine. Then you insert 3 into the array.
Okay.
Then you come back and say, now let me figure out for 4, what's the way of insert in the tree and what's the best number when XORed amongst 1, 2 and 3 with 4 that will give you the better answer.
Okay.
And then you insert 4. Then you go check with 80 for 80, you check and so on. The reason why this will work is because if for example, if your best answer was like say like 35 XOR 80 was the best answer or something like that. Right? Let me actually do 65 and 64 were to be here, right? 64 and 65, and let's assume that this 2 was not there. Okay. So the best answer is essentially 64 XOR 65, correct?
Right.
Nothing else. So what happens is when you do 1, you don't have anything in the tree, so you don't find anything. So 1, no answer. 3, the best answer is 1. So 1 XOR 3 is the best answer. For 4, 1 XOR 4 is the best answer. Correct?
Right.
And then for 64 XOR 4, XOR 3, XOR 1. 64 XOR 1 is the best answer.
Right.
for 64, like with 64, and then you can compare against the other numbers as well, right? The best so far is obviously 3 XOR 1.
Correct.
3 XOR 1 is 2, 64 XOR 1 is 65, so the best answer so far is 3 XOR 1. Correct?
Okay.
Then you have inserted 64 in the tree. Now when you're trying to process 65, you will find that 65 XOR 64 is the best answer because it gives me 1, which is better than 3 XOR 1.
Right. Okay.
Right? So I didn't find the answer with 64. I only found the answer with 65 because when 64 was being processed, 65 was not in the tree.
Right.
When 65 was processed, 64 is in the tree. So at all possible times, you're only looking at what is the best answer I can do with all the elements to my left. And you will always find that this will eventually result in a solution.
Okay. Okay, I get that.
Okay. So this is just another way of thinking about this. Any questions? We are at 8:30, so I will be stopping in another minute or so. Any questions before we park for the end of the day?
No, if it is for 4 XOR some kind of it, then it will be super typical, I think.
Multiple XORs, like 2 XOR, 3 XOR, 4 XOR?
Yeah, M XOR. Like the Twosome Problem, M problem.
I will leave that as homework exercise for people to figure out. I haven't actually spent time thinking about it, so I'm gonna save by the bell at this point of time. So,
can you as you were writing, I followed a bit, but then didn't get to copy everything that you wrote on the notepad. Would you be able to share that?
The Etherpad is available for people to actually copy, so you should be able to go to the link and copy it yourself.
Okay, perfect.
Just go to the. Let me stop the recording and then we'll let me just chat for a few minutes. Thank you, everyone.